Okay, so let's continue. So now I think before the break, like we were looking at transfer learning and multitask learning. So we're going to see like few more learning paradigms. Okay, so the next learning paradigm is the idea of few shot learning or one shot or zero shot learning. Okay, so now this whole learning paradigm is based on the concept, like based on the motivation that we discussed before, that humans don't require millions of images to learn to recognize a cat, for example, right? Like, so on the other hand, okay, so humans don't require millions of examples. Okay, on the other hand, like the current generation AI systems, okay, so they often require millions of examples. Okay, so why is this the case? Like, so this is the case for several reasons. Okay, so the first reason, the most prominent reason, is gradient descent. The most the central learning algorithm that we have seen in this course, like, is actually a very slow learning algorithm. So you have the concept of step size, and like you have to take like tiny steps every time, and it's going to take at least like hundreds of iterations for gradient descent to reach the place where it wants to reach. Okay. Now there are other reasons for why they require millions of examples. The second is most of them are standalone systems. Okay, which means there's no way to knowledge transfer or to transfer knowledge. Okay, and also the third difference between humans and AI systems is these AI systems actually still deal with low level inputs than abstracted inputs. Okay, to give you an example, like when a computer vision system looks at the image, it is looking at the image as a set of pixels, right? On the other hand, like when you look at the image, you have a much more higher level of abstraction. Like, so you see the objects, you see the connection between the objects, and probably you would even already make prediction about what is happening in the scene and so on, right? Like, so you have like way more information and like a structured way of processing these kind of inputs than the current generation system. So these are reasons why they require a lot of examples. Okay, but the goal of few shot learning, okay, is to learn from as few examples as possible. Okay, now one shot learning is an extreme case of this. In the case of one shot learning, I want to learn a task from only one example. Okay, now an even more extreme case is zero shot learning. Okay, where I want to do a task without seeing any example. Okay, to give you an idea, like let's say I have learned to play like one video game. Okay, now I'm not showing you what the second video game is, but I will give you an explanation of how it is going to look like. Okay, now just this explanation without any example, like you can easily go perform well in the second game, like even though you have never played this game before. Now this is an example of zero shot learning. Okay, now again, like all these types of few shot or zero shot or one shot are not possible without some form of transfer learning. So that's why I say that all these learning paradigms are interconnected. Okay, so there is a question, does it work with unsupervised learning? Yeah, so well, like I will let you think about it. So unsupervised learning is definitely one way to go few shot, right? Like, so you do a lot of unsupervised learning so that you have a really good system that could pick up simple, like pick up new task with just one or few examples. Okay, so you can definitely use unsupervised learning or semi-supervised learning or even supervised learning to do these tasks. Okay, now let's move to the next paradigm, which is the idea of online learning. Okay, so in the case of online learning, there is no separate train and test data. Okay, also the agent can never see the same example again. So you can also consider this as a streaming setting, where you go deploy a machine learning system in a setting. Okay, now it sees the first example, it has to like make a prediction. Then it sees the second example, it has to make the prediction and go on and so on. Okay, so now there is no separate training phase, which means that every time it makes a prediction, it should try this kind of system should learn as fast as possible, because you cannot make a lot of errors while learning, because learning, there's no separate learning and separate testing. Like learning is happening while performing, like, right? So that's the big difference between online learning and traditional batch learning that we have seen so far. Okay, now in this case, x, the input x comes in an infinite stream. Okay, an agent makes prediction for y. Okay, so once you make the prediction, it is going to learn, like it receives the true y, then it continues. Okay, now this kind of setting requires systems which are able to learn faster and make as less mistakes as possible during learning. Okay, now to give you, okay, so these are also, there might also be situations where like you cannot, okay, one hack for doing online learning is like as you receive more and more example, you could collect these examples, save them, and then you do mini batch gradient descent using these examples, right? Like, so that is possible. That is one algorithm to do this online learning. But often like you might be in a situation where either the data is too much that you cannot save all the data, or there are privacy concerns that you cannot save any data without the user's permission, right? Like, so in those cases, pure online learning is the solution. Okay. Okay, so there's a question. Overfitting is the most common challenge in one-shot learning. It is definitely sorry. It is definitely a problem, right? Like, so you have only one example. You want to learn a meaningful function from one example. So yeah, it's definitely a problem. Okay, so now let's move to the next learning paradigm, which is the idea of active learning. Okay, so now active learning focuses on situations where getting labels is costly. Okay, so if getting labels is costly, like it again, like it could be the medical application where like every labeling requires like costly tests to perform, right? Like, or it could be like a complex industrial application where labeling something requires huge domain expertise. Okay, and maybe like we are lacking in the number of domain experts. Okay, now in such situations, like we could use active learning. So the whole idea behind active learning is you have an agent, okay, and you want to train this agent. Okay, now you just give the agent probably with a bunch of x and y and a lot of unlabeled examples. Okay, now this agent is going to choose an x and ask the human for label. So it's going to actively ask the human, oh, okay, what is the label for this x? What is the label for this x? Okay, now this human can give labels, and the goal of this agent is to ask as few labels as possible to achieve the target performance in the task. Okay, now the whole idea here is like, so we have an actively learning system which chooses which X to label, simply because labeling might be a costly affair in the problem that you're working on. Okay, so is there any questions before we move to next? Like labeling clusters, yes, it is like labeling clusters. Like, so a simple strategy. Okay, well, I said I will not talk about solutions, but a simple strategy could be based on what Simon mentioned, right? Like, so, like you could take all these X, you could cluster them, and then ask the label for every cluster centroid or cluster mode, right? And use that as a label for all the examples in the cluster. Now I have given you an algorithm for active learning, right? Like, so now this is probably a naive vanilla algorithm. There are hundreds of algorithms on like how to improve on this. Okay, any other questions? Okay, so then let's move to the next learning paradigm, which is the idea of lifelong learning. Okay, so which has several names in the field, like it's also sometimes called as continual learning. Okay, or it is also known as never ending learning. Okay, so the whole idea of lifelong learning is to have a single agent which is going to learn a sequence of tasks over its lifetime. Okay, I have a single agent. Now this agent is going to learn a sequence of tasks during its lifetime. Now, this is actually very similar to human beings, right? Like, so we are lifelong learners. Like, so we learn about something today and we learn about something else tomorrow, and like we keep learning new things and we connect dots between these different things that we are learning, and like we develop our knowledge and become experts in fields, right? Like, so now that is what we are trying to mimic in lifelong learning. Okay, so now such a lifelong learning system should have a bunch of characteristics. Like, for example, you should be able to retain the knowledge it has learned so far. Okay, and then it should be able to selectively transfer knowledge to learn new tasks. Okay, and you should also ensure effective and efficient interaction between 1 and 2. Okay, okay, now here is a question for you. So let's say I have a neural network. Okay, and I'm going to use this neural network to learn a series of tasks. Like, I'm going to use this to learn task 1, task 2, task 3, and so on. I could learn 100 tasks, or I could learn even 1,000 tasks. Okay, now what are the challenges in training such a system? Like, what are the challenges I would face in training a neural network to learn a bunch of tasks in sequence? Okay, remembering the task is a challenge, right? Like, so when I'm learning the new task, I should remember the previous task. Now, why would the network forget the previous task? It has already learned it, so why would it forget? Okay, no, that's not an answer. Yeah, so your parameters are going to change when you're doing gradient descent for the new task, right? So okay, the first reason is parameters are changing, which means there's a possibility that you might forget the previous task. Is there any other reasons that you would forget the previous task? Well, I have put a 2 here, so there has to be a second reason. Now, think about the capacity of this neural network, right? Yeah, not enough memory. Well, Charan, you should not answer. Okay, so not enough memory, right? So let's say I have a neural network which has 1 million parameters. As I learn every new task, I'm going to use some of these parameters to learn this task, right? So now if I learn, let's say 100 tasks, I might have already used all the million parameters. So when I learn the 101th task, I have to unlearn something to learn the new thing. So this is the issue of capacity. So these two reasons might lead to what we call as the catastrophic forgetting. Okay, so how to solve catastrophic forgetting in a machine learning system is what the central problem in lifelong learning. Okay, I think Masood is giving us a solution, like maybe save the model before transferring. Yes, that's one algorithm. But there are hundreds of ways to solve catastrophic forgetting. Like I would encourage you to come up with your own algorithms and then go back and learn about these topics. Okay, so finally, like I would like to talk about the 10th paradigm, which is the idea of meta learning. It's also sometimes called as learning to learn. Okay, so this is a fancy problem where like we are going to learn to learn. Okay, now this is kind of related to continual learning, but it is slightly different. Okay, so the whole idea here is I'm going to give you a bunch of training tasks. Okay, so this is my task 1, this is my task 2, this is my task 3, and so on. Okay, each task by itself has some training data and test data. Okay, now I want to design a system which will learn to solve all these training tasks, okay, in such a way that given a new test task T4 or T5, okay, so train test, okay, given new tasks, this agent can perform well on these test tasks. Okay, or in other words, I'm asking the question of how can I learn to learn efficiently, right? Like, so how can I learn to learn these 3 tasks in such a way that given new tasks, I could learn those tasks easily. Okay, so it's like one level higher in terms of learning. That's why we're going to call this as meta learning, okay, or learning to learn. Okay, so finally, like as I mentioned before, there is no clear boundary between many of the settings described so far. Okay, so some of them would require some of the other capabilities by default.
And Sharath, isn't meta learning usually with a few shot setup only?
It need not be. Okay, so I think that concludes our discussion on like different uh, frontiers in machine learning. Okay, so I would repeat again, like so the goal here was not to solve any of these problems. So the goal here was to introduce you to these problems, and now by the end of this course, like you are equipped enough to go and learn about these problems by yourself, and even come up with a solution for these problems by yourself. Okay, any questions about this so far before we move to the next part? Okay, so what could be the gradient here in meta learning? So that is a good question. Well, again, as I said, I don't want to give solutions here. So for example, like one gradient could be like, what is the generalization performance in each task, right? Like, so I want a system which will have high generalization performance. Now I can compute a loss function based on this generalization performance and compute gradients. So if you want to learn more about that, like I would recommend you to check MAML, which stands for model agnostic meta learning, which is a gradient based solution.
I'm also putting a link to a blog, Sarath, which has like good details of all the meta learning algorithms.
Okay. Okay. So any other questions? Okay. So now we are going to like like briefly talk about what next, right? So let me share some slides. Okay. Okay. So what next? So there, like I have, okay, I will make these slides available after the end of the lecture for your reference. So, well, first of all, you need to finish your Kaggle competition and the exam. Okay. So I assume that this is advice for you after you finish your course. Here I have listed a bunch of useful reference books, like if you want to learn more about machine learning. So Tom Mitchell's Machine Learning, Christopher Bishop's Pattern Recognition and Machine Learning, Hasty et al.'s Elements of Statistical Learning, and Murphy's Machine Learning, a Probabilistic Perspective. So these are all also the references for that we use briefly, but like, so there are hundreds of other topics in these books which we did not touch in this course. And data mining, which is a very related field to machine learning, um, shares a lot of algorithms and ideas with machine learning. So these are the two useful and like most important data mining textbooks, which I would highly recommend. Also, there is this mining massive data sets, which is also very uh, useful if you are interested in scaling up your machine learning algorithms or data mining algorithms to situations where you cannot train them with a single machine and so on. Okay. Um, okay. Yeah, I will talk about courses. Don't worry. Okay, so and in terms of graphical models, like there is Daphne Coller's graphical models textbook, which is a pretty standard book for like reference book. And for neural networks, I like this old neural networks book, which only talks about things up to 90s. But then there's also this recent deep learning book by Goodfellow, Benjio, and Corwell. And for reinforcement learning, Rich Sutton's and Antobato's like reinforcement learning textbook is kind of the primary textbook for the field. And finally, like if you are interested in AI, like if you're interested in having machine learning as your career in the future, I would highly recommend you to read Russell and Norwick's Artificial Intelligence book, which I think has a new edition right now. It's such an extensive book, which gives you the breadth of the field. So it's also like really um, enjoyable reading. So I would highly recommend you to read Russell and Norwig if you care about AI. Okay. Next courses, as someone asked. So I'm using this slide only to talk about courses which are outside Poly, simply because you already have access to courses inside Poly, right? Like so, like I would recommend you to check AA concentration at Poly for undergrads, which lists all the AA courses, and you also have access to the courses that are happening at like at the GAGL department, right? Like so for example, Chris is teaching a follow-up course in winter. I'm not sure if the course is offered next in this winter, but you can check. But there are also a lot of machine learning courses offered at UDM, HEC, and McGill. Okay. Now, most of these machine learning courses are integrated in the Mila website. Yes, almost all the courses are in English. Like if you go to McGill, definitely all the courses are in English. I think all the machine learning courses at UDM are English too. HEC might be French. Okay. But yeah, so you can go check Mila's website, which is I think Mila.Quebec, and you would see the list of fall and winter courses. Okay. And also, I will be teaching a reinforcement learning course next fall. So not winter, but fall 2021. Other than that, there are like a bunch of follow-up courses outside Poly that I would highly recommend. So for example, in the winter, there is the deep learning course at UDM, IFT 6135, which is a proper follow-up for like this course. And there is also probabilistic graphical models at McGill, which is also offered at UDM in next fall, in case you cannot take it in winter. Then there is optimization and structure prediction course at UDM, and there is also an NLP course at fall. But we like in McGill, but we also have an NLP course at Poly, so you would see that in the A concentration. And there's also this course called Duckytown at UDM, which is about self-driving cars. If you're interested in self-driving cars, yeah. So I think do I have anything? Yeah. So also, well, as someone rightly pointed out, there are hundreds of online courses available. But here is a list of courses that I think are very useful and something that I have seen by myself, and also like I recommend to all my students who start with machine learning. So there is a reinforcement learning course by Professor Balaraman, and also there is one by David Silver. So the first oral course is like more classical. David's course is more deep learning slash reinforcement learning. Then there is also an excellent course on neural networks by Hugo Larachel in YouTube. There's also one by Jeff Hinton in Coursera. And Daphne Coder has a probabilistic graphical models course in Coursera as well. And I think the course website already lists these three basic courses on convex optimization, probability theory, and linear algebra, which are very useful background to develop if you are considering a serious career in machine learning. Okay, so I think that is it. So we are done with this course, at least in terms of lectures. So you still have to finish the Kaggle competition and the exam. Again, like I would like to thank all of you for uh, like being part of this journey for this semester. Like, so this, as you all know, this is my first semester at Poly. This is my first semester as a professor. So there were a lot of new things that I learned. Also, COVID added a lot of things on the top of the usual things, right? Like, so like how to teach remotely, and like still how to make students engage in a remote class. Like, so these were very challenging, and I think I tried my best. So definitely next offering will be much more next offering will be much more improvised, and I should thank you guys for that. Like, so like all your feedback is going to help me to give a better course for like 100 other students next semester. Thank you.
There's some questions in the chat, sir.
Okay.
What type of questions in the exam are we going to have?
Okay. So for the exam, like as I mentioned before, you are expected to study all the lecture notes, like the chapters in the lecture notes, and try answering all the self-assessment questions. So if you can answer all the self-assessment questions, then you should be able to answer the type of questions that are asked in the exam. It's going to be a bit more difficult than them for sure because it's online, but that is a good enough preparation.
Handwritten or computer-based solutions?
You can do whatever you prefer. So you have 2 hours time plus an extra 1 hour as a you have totally 3 hours. So you could either handwrite, scan it, and upload it, or if you are too fast in typing, you could type. You could even do a mix of both.
And maybe Sharath, you can also guide them to check out NeurIP's conference if anyone is interested.
Yeah. So there is NeurIPS, which stands for Neural Information Processing Systems. Like one of the premier machine learning conferences happening this week. I think, well, I know all of you are going to be busy with your end of term assignments and exams and stuff. Uh, Probably in a couple of weeks, they are going to release all the talks and videos. So you could check them out. All the chapters included, yes, because we have given chapters only up to lecture. I think 15 chapters includes up to lecture 23, which is what is that in exam. We will be using Gradescope for exam, yes. Thank you, thank you. Thank you, everyone. Yeah, as I said in the beginning, like we will release A3 today. For the Kaggle competition, like we would give grades. The 30 percentage will be distributed based on the ranking. And once we have the clear ranking and like once we finalize the scheme, like we will let you know. Yeah, I know that there's always going to be a crowded effect, but we will try to decrowd the ranking. Okay, so maybe I will stop the recording.